PW lab. First I will tell you the safety precautions when you are performing the experiment. Always remember you should use the hand gloves, and these hand gloves are not practical for low voltage, and for low voltage also it is not applicable. So better you use if it is a high voltage circuit. In single phase circuit it may not be required. Now I will tell you about the single phase circuit. Here, as you know, the specification of single phase voltage. So first always remember, between phase and neutral you will get 230 volt AC supply. Now we measure it using multimeter. So always remember your multimeter probe you should connect to voltage range, not on the ammeter range. If you connect it ammeter range, then as you know ammeter is a short circuit, and if you directly connect across the 230 volt, then what will happen? There will be a short circuit and this will be. So here always remember you should connect it between line and neutral, that is the voltage and neutral. Then with red and black wire connect between the phase and neutral. So here you should get 230 volt. When you connect it between earth and phase, then also you should get 230 volt. And always remember, while checking the earth connection, whether earth is properly connected or not, you should keep it on, do the connection between earth and neutral. Between earth and neutral you should not get 0 volt. If you are getting 0 volt, that means earth is not properly connected. Around 2 volt you will get. If you are getting less than 2 volt, between 0 to 2 volt but not 0, that means earth is properly connected. So here I am getting 3.7 volt. It is okay because it is less than 5 volt. So earthing is done properly. Now we see the experiments on DC supply. Now in DC supply, here neutral which we are using is for DC, it is from DC rectifier. So there are less chances of getting shock. Now what do you mean by shock? When you connect to the phase, that time current will flow to your body. Your body will act as a resistance, and because of I square R you will get a shock. That is in case of AC. But here in case of DC, neutral is isolated. So here less chances of getting shock. But better take precautions and don't touch the positive voltage of the DC supply. Now here positive and negative supply is given, and this is the connection about a DC motor, DC shunt motor. Here the rating is given 2.2 kilowatt, 220 volt, 12 ampere. That means your load should not exceed this current. If you are increasing the load, your mechanical load is connected. So mechanical load if you increase, and if your current rating is going beyond 12 ampere, then motor will get damaged. So 12 ampere, that is the armature current, and that is same as the load current because it is a DC shunt motor. Now this is a symbol for DC shunt motor. As I told you, DC shunt motor means there is a field winding and armature winding. So this total is symbol for DC shunt motor. Now here field winding and armature winding is there. We already performed an experiment on finding the resistance of armature winding and field winding. So as you know, the field winding resistance is high compared to the armature winding, and armature current is nothing but a load current. So here this is a basic diagram. So instead of using this diagram and doing connection here, you can directly connect ammeters on the table. So that is feasible. Now here from positive supply, I am connecting 2 ammeters because I want to measure 2 currents. One is the armature current and second is the field current. So I will require 2 ammeters. One is the armature, one to measure armature current, and second to measure the field current. Now as you know, armature current, it depends upon the load. So I connected armature current of 0 to 10 ampere rating, and field current ammeter, that is small rating 0 to 1 ampere or 2 ampere. So here it is connected to the 2 ampere. Now I want to check the speed characteristics, that I will increase the armature voltage or I will increase the field current, and I will check what is the speed. So as you know, there are 2 methods to control the speed of DC shunt motor. One is using armature voltage, second is using field current, that is the flux control method. So these are the 2 basic methods. First we will see about the armature voltage control. So armature control voltage means you have to keep field current constant. So I will keep field current constant at some rating, say 0.6 ampere, and then I will increase the armature voltage. Now how to increase the armature voltage? So one rheostat is connected, so this rheostat is connected in series with armature resistance, and this resistance when I will change, armature voltage will increase or decrease. So depending on that, armature motor speed will change. So as I increase the armature voltage, so increasing armature voltage means resistance value should be low. So as I increase the armature voltage, speed will increase. Same way, I will in the next table I will keep armature voltage constant and I will increase field current. So to increase or decrease the field current, one more rheostat is connected. So using that rheostat, I can control the speed of DC shunt motor. So as you know, in DC shunt motor, field current is inversely proportional, that is flux. Flux is inversely proportional to speed. So as I increase the field current, speed will decrease. And in armature voltage is linearly proportional. So if I increase the armature voltage, speed will increase. Now, here these are the two methods. So I will start the connection. Now always remember your motor should start at low speed. So at low speed is what? As you know, armature voltage is directly proportional. That means I should keep less voltage at start. So armature voltage should be low. So this rheostat should be at maximum position so that more voltage will drop across the rheostat and less voltage will drop across the motor armature. Field current should be low. Field current should be maximum. So field current should be maximum because field current or flux is inversely proportional to speed. So I will keep rheostat at 0 position. So this is a 0 position for rheostat. See how it is connected. Now I will start the connection. See, motor is started. See, at start motor takes more current. At start motor takes more current and again it will come to the normal position. So even though motor is rotating at high speed, armature current will not change, armature current is fixed. Again I will switch off the motor and I will start. So you will come to know that how the speed armature current is more at start, and that is because of inertia of the motor. See, the motor I will start, when I will start it, see it will go to the maximum position and again it will come to the normal position. So that starting current, that is more current because motor is starting with a high inertia and because of large inertia motor taking more current. Now we start the experiment. So if I increase the armature voltage, I will keep it on DC voltage range. So this is a DC voltage. Now I am increasing the armature voltage, and as I increase the armature voltage, see armature speed is increasing. This increasing speed I can measure it in a tachometer. See, from the noise of the motor also you will come to know that speed of the motor is increasing. Again, field current. Now if I increase the field current, if I decrease the field current, see the motor speed is decreasing. Now this increase or decrease speed current you can measure using a tachometer. So we have tachometer. So tachometer, there is a switch to switch it on. Then it will show 7 means by default that meter is working. Don't press this switch because it goes into the memory. If by mistake you press, then again you reset it, turn it off and again turn it on. Now while measuring the speed you should press this switch and then measure the speed. So you will come to know what is the speed of DC shunt motor. Like that you can prepare a table for speed and armature voltage or field current. Then plot a graph. You will get a linear characteristic straight line for speed versus armature voltage, and for flux, that is the field current, and speed if you plot. Then as you know these are inversely proportional, that means speed is inversely proportional to x, that is speed is equal to 1 by x, so constant divided by x. That means you will get exponentially decreasing characteristics when you are controlling using field current.